Okay, good morning, everybody. So, a couple of classes ago, we began discussing dynamical systems. So, we began with linear dynamical systems defined by the equation x dot equal to ax. It's very simple to analyze, and we found out how the dynamics depends upon the eigenvalues, right? And we looked at some simple classification of different kinds of fixed points. The origin is a fixed point, and we also have drawn the bifurcation map. Then we began discussing nonlinear versions, but in two dimensions, with the help of what we know as the phase plane. So then once we understand how phase plane works, we said you need to first find the fixed points and then study the stability and classify the fixed points, and then based on that you can find out the overall vector field, right, on the phase plane. Then we said one of the very important things that you need to study in a phase plane is a limit cycle. The limit cycle is basically a periodic solution, how the trajectory tends towards a periodic solution, and that kind of a periodicity is very relevant to understand neuronal dynamics, because we said that neural firing is periodic, right, and also it has a fixed amplitude. So in that sense, it is different from a simple harmonic oscillator. So then we said we'll look at three kinds of, right, we'll approach limit cycle from, in three ways. One is we'll look at one specific system, the example of a limit cycle. How do the equations look, right? Because a limit cycle, there's no general formula. Given any system, there's no general way to find out whether it has limit cycle. So there are several theorems which can give you that result, which can say something about that that issue. So let us start with we began with these special systems. We specifically looked at these two equations, x dot equal to that and y dot equal to that, and then we have shown that if you convert this into polar form, right, you get two equations. One is dr by dt is equal to mu into r into 1 minus r square. So in this equation, r always tends towards 1, whether it starts from less than 1 or greater than 1, it always tends towards 1. And this equation theta dot equal to 1. So therefore, basically, it represents a rotor, right? A point moving on the unit circle at a uniform angular velocity. So that's a limit cycle. So no matter where you start from, you'll always tend towards that point. Now, I just want to point out here, although we derived this last time, I want to point out that it is possible to get this result only because of the nonlinearity in the equation. Without the nonlinearity, you won't get limit cycle. So let me show that here. Right, so we have started with this equation at the top, right? Dz by dt is equal to I omega z plus 1 minus mod z square times z. So the nonlinearity in the equation comes because of the second term, this mod z square times z term, which is a cubic nonlinearity. So now if you take z equal to this and so remove the nonlinearity, right, and then just take the linear part, dz by dt is equal to I omega z. Then what happens is you can expand z into x plus iy, so you get this, right? And so you get dz by dt is equal to omega y, right? And dy by dt is equal to minus omega x, right? And therefore the Jacobian, this is a linear system. The Jacobian A is simply 0 omega minus omega 0. So the eigenvalues of this is plus or minus I omega. So it's a center, which means it's a simple harmonic oscillator. So what I'm saying is, it is as though you start with a simple harmonic oscillator and add a nonlinear term, which makes it a limit cycle. So it's just a way of saying it, but basically what I want to point out is limit cycle can only be obtained in a nonlinear system, not in a linear system. The nearest that you can get in a linear system is a center where the eigenvalues are all purely imaginary. Okay, so now let us look at the second kind of approach to understand or find out if a system has limit cycles. So for that, we'll introduce the Lienard systems. So what this theorem says is, if you have an equation of this form, okay, is the x double dot plus f of x times x dot plus g of x equals 0. So note that it is a second order system and nonlinear system. So since we have been talking about phase plane, we have been dealing with two first order systems, right? So because we have two variables x and y defining the dynamics. So to convert to that form, what we do is make the simple substitution. We define x dot equal to y, then y dot comes here, then x dot is y, so you get y dot is equal to minus g of x minus f of x y. Okay, so now you are able to describe the system into two first order systems, but nonlinear. So what the Lienard theorem says is that if you have a system of this form, whether upper form or lower form, then f and x, f and g, the function should have certain properties. F and g are continuous, of course, and also differentiable for all x, right? And g must be an odd function. Okay, therefore g of minus x is equal to minus of gx, and also g of x should be greater than 0 for x greater than 0. So that is another further condition, right? It's not only odd, but it should be g of x should be positive for x positive. Then f of x should be even function. That's another condition. Then if you take the definite, the indefinite integral of f of x as integral 0 to x f of x or f of u du, this function defined as capital F of x should have exactly one positive 0 at x equal to a, some positive 0, let's call it a, and it should be, so it should have 1 0 at a, and it will have 1 0 at 0 itself. You can easily see that here. So between 0 and a, it should be negative, and it should be positive and non-decreasing for x greater than a. That means for f of x should tend to infinity as x tends to infinity. So lots of conditions on this f of x, both small f of x and therefore on capital F of x. Okay, so then if all these conditions satisfied, such a system will have a unique stable limit cycle surrounding the origin. This is what the theorem says. It's given in Strogatz. You can take a look at that. So one example system which has this Lienard system kind of properties is a famous oscillator model, a nonlinear oscillator model called the van der Pol oscillator, right? And this oscillator is defined by this equation: x double dot plus mu into x square minus 1 times x dot plus x equal to 0. So in this equation, you can see that f of x is this part, okay, mu into x square minus 1, and g of x is this. So you can see that f of x is an even function, g of x is an odd function, and g of x is positive for x greater than 0. And if you look at integral of f of x from 0 to x or 0 to u, right, you get this expression, 1/3 into mu x into x square minus 3. If you plot this function, if you can plot it here, it looks something like this. So I'm not showing it on the left side because it's an odd function. You can see that's odd function. Right, the same thing you will have a mirror image, not a mirror image, but it's a kind of inversion of this. So it looks something like this, goes down like that. So you can see that on the positive side, it has only 1 0 at this point a, and a will turn out to be root of 3 because this a is 0 corresponds to the x square minus 3 equal to 0 term. So therefore, a is root of 3. And between 0 and root of 3, this function is negative, and beyond root of 3, this function is positive. And not only that, as x tends to infinity, f of x, right, tends to infinity. So all the conditions of Lienard theorems, system theorem, is satisfied by this oscillator, and therefore the theorem basically says it's an oscillator. It will oscillate. Okay, so now the proof is very difficult. I'm not going through the proof, but I'll just give you a demo. Right, I'll show you. Do a Matlab run. So can you see the Matlab screen, Sandeep?
Yes, sir. We can see the screen.
Yes. Okay, great. So this is a code that Sandeep has written. Right, it simulates the Lienard, the van der Pol oscillator. So there's a parameter called mu, if you remember, in the f of x term. I'll start with actually 0 mu. So that makes it actually a linear system because nonlinearity is coming from the first order term, x dot term, and that factor is mu. If I make it 0, it becomes linear. It becomes simple harmonic oscillator. So let us see what happens if you run it. Okay, and you get a perfect sinusoid, right? And it goes round and round in a circle, right? Which is what is expected. So now let us make mu slightly positive. Right. So you see that already, if you start from some point, it goes round and tends toward that circle. Right. In fact, if you, in the previous case, if you just take mu0 itself and run it, so x equal to 1. So x equal to 1, let me say x equal to rand 1 comma 1. Okay. So that you can start from anywhere. Right. It'll always be a circle. See, the amplitude is some 1.3 or something. If I run it again, amplitude mu is 0. Yeah, every time you run it, you should get a different amplitude. Right, this time it is 1, so and so on. So it becomes, it's a simple harmonic oscillator. So the amplitude is not stable. Right, now you take a slightly positive mu. So no matter where you start from, right, you always go to that particular amplitude. Here it's about 2. So if you run it repeatedly, and you always go to the same amplitude. That's the hallmark of a limit cycle oscillator. Then let us try bigger and bigger values of mu. So you see that for small mu, it is looking like a nice sinusoid. But as mu is increased, this in the phase plane, the loop is becoming more and more distorted. It's moving away from a circle. It's looking more like a kind of a smoothened rectangle, right? And even the waveform of the oscillation, right? It's no more a sinusoid, right? It's very distorted. So in fact, this waveform looks a lot like some of the oscillations of cardiac cells. So there are a lot of cells in the body which have oscillatory properties, right? So cardiac cells are certain cells in the heart which are called pacemaker cells, which are what are constantly driving your heartbeat, irrespective of even without nervous input. The heart can beat on its own. That is driven by certain cells in the heart called pacemaker cells. And their waveform looks a lot like this. In fact, Van der Pol oscillator has been used to model cardiac oscillations of this cardiac pacemaker cells. So you can see that here, and as you go higher, it will be even more distorted. Okay, you see that this is looking like a very nice cardiac action potential. Okay, just by increasing the distortion, increasing mu value. Right, so that gives an idea of how a limit cycle behaves. Let us go back to our discussion theory. Okay, so the next theorem, so that is Lienard systems. So next theorem, which tells you under what conditions you can have a limit cycle. It's called the Poincare-Benedixson theorem. So here also, let me to motivate this, right? I'll just present some simple arguments using your Sandeep, how do you get what is it called, the drawing tool, right?
Okay.
Shit.
Well, I think in the Google Meet we don't have the drawing tool.
Oh,
We
that's only in Zoom, is it?
Yes.
Okay, let me
No,
try
we can
something.
paint or any other.
Okay, fine, I'll do that. Okay, you can see the paint screen, right? Hello?
Yes.
Yeah, okay, cool. So basically what this theorem says, I'll give an intuitive idea, then I'll give it a more formal definition. Suppose you have a limit cycle, right? So no matter where you start from, you always go towards it. If it's a stable limit cycle, so wherever you start from, it will always tend towards that, whether you start from inside or outside. Now look at this. If you start from inside, right, no matter what you do, you will never get out of the limit cycle, because there is no trajectory that will lead out like that. If you start from inside, you will never be able to go like that. If you do that, then the two trajectories are intersecting. And we know that in a continuous vector field, you can never have two trajectories intersecting, because when they intersect, what that means is, right, there is no, at that point, there's uncertainty. You don't know which way to go. Whereas the equations are very definite, they're deterministic. So from a given point, you can only go in one direction. So therefore, that possibility is not there. So what that means is, if you have, if there is a limit cycle, then if you start from inside, you always stay inside. So you are trapped inside this region. And that's what it means. So conversely, if there is a region in this state space, in the phase plane, where you are trapped, that means if you, all vectors inside that, right, will not let you go out of this region. Right, and the vector field in the inside this, as I said, it won't let you go out of this region. Right, then it means it's likely that there is a limit cycle somewhere there. But to give an analogy, right, when people study space, right, and so suppose there's a black hole somewhere, what is the indication of that? You won't see any light coming from that part of the thing. So you'll see light in the nearby areas, but there's no light coming from that place. So there's a possibility that there is a black hole there. So similarly, if you can find a region in the state space from where once you are there, you can never get out, right? It means it is likely that there is a limit cycle there. But point is, there's a small catch here. You can have such a region even without a limit cycle if you have a stable point, a stable node or a stable focus. If it is a stable node, everything straight goes towards that. Okay, so therefore, also if I am somewhere here, I'll never go. I'll never be able to leave that space. Similarly, if I have a stable focus also, I'll kind of make a more curved spiraling motion into that point. In this case also, I'll never leave that place. Okay, I'm trapped. But obviously, a stable node or stable focus is not a limit cycle, right? That's the total opposite of a limit cycle. So now what do we do? So therefore, what people actually do is to prove a limit cycle, you construct show that there is a certain region in the state space, which is like an annulus. Okay, and this annulus, so you have to have two borders. The region has to have two borders. I'll call this region R. And you have to show that for the outer border, all the flow leads you inside. Right, that means the vector field on this contour, all the arrows should point inwards. Similarly, for the vector field on the inner contour, all the arrows should point outwards. Okay, so what that means is, if it is how, so if you are able to find two contours like that in the phase plane somewhere, in such a way that on the outer border all the arrows point inwards and inner border all the arrows point outwards, then what it means is, within R, if you start from within R, right, you will never be able to leave R. Okay, this is one condition. The second condition is, just to avoid this possibility, this fixed point business, the second condition is there should not be any fixed points inside R. Okay, so to summarize, find a region in state space, call it R, and it is defined by two, it's like it should have an annular form, so an outer contour and inner contour. On the outer contour, all the arrows should point inwards. On the inner contour, all the arrows should point outwards. Then it means you are trapped inside R. So, and second thing is, you are trapped, but you have to keep moving, because if there are no fixed points inside R, right, then you have to keep moving. Only at fixed points you tend to move, you tend to stop, if at all. Right, even fixed point, if it is a unstable one, If you are on the fixed point, you will stay there forever, but if you are pushed off a little bit, you will move away. Suppose there is no fixed point at all, you have to keep moving. So it's a very interesting thing. It's like, you're caging an animal, right? You hunt it and corner it and put walls around it. So you find two walls to it. Outer wall will make sure it won't go out. Inner wall will make sure it won't go in, right? And therefore it is confined, trapped within this annulus. And the fact that there is no place to sit, no fixed points, so it has to keep moving. So one possibility is it can keep on moving randomly like that, without ever repeating itself, no, not periodically. Now the mathematical theory says that that's not possible. That option is not possible. So the only option left for the system is to go round and round in a loop in a periodic fashion. So that's what the theorem says. Okay, so to summarize, if there in the system, if you can show that there is a trapping region, so if in the system there is a trapping region in such a way that, right, so there is an outer contour and the inner contour. So this is outer one, and this is inner one, right? In such a way that flow on the outer contour is always inwards, flow on the inner contour is always outwards, right? Then the theorem says that there will be a loop, right, which is a periodic. So this is a solution which is periodic, and the system will be confined to that closed trajectory, loop trajectory. Okay, so if R is a closed bounded subset of the plane, which is devoid of any fixed points, and then the theorem says that, and also there is this trajectory C that is confined in R. That means if it starts in R, it stays inside R forever. If this is true, then there is a C is a closed orbit. There is a closed orbit inside that region. So how do you do that? For a given system, then you have to somehow figure out, construct two contours so that on the outer contour all the arrows point inwards, and the inner contour all the arrows point outwards. So normally when there is a theorem, suppose you want to test if a system has limit cycle, you should have a very well-defined algorithm, right? You just follow those steps strictly, and then you should have the answer. But the Poincare-Benedixson theorem is not that kind of a theorem. It involves some construction for which there is no formula. If you can find a contour with these properties or two contours with these properties, then you have the limit cycle. But it's not easy. There's no simple way to find out, or construct such contours. Because to be able to construct such contours, we should be able to understand the vector field everywhere. And you can't go, you can't plot the entire phase plane, manually, which is very difficult. Okay, so but there are some tricks that you can use to find out what is the general direction of the vector field in any part of the state space. So that is not very hard to do, okay, because fortunately with the null line business, for most simple functions, you can find out what is the general direction of the vector field in any given part of the phase plane. So to understand that, we need to get used to these tricks because we'll be using it, in future also. Let us first do it with a very simple system, which is linear, and then we'll do it for a nonlinear system later. So let us take this system, dx by dt is equal to x minus y, dy by dt is equal to x plus y. Okay, now we need to find out what is the direction of the vector field everywhere in this plane, in the xy plane. So how do you do that? The procedure is standard. First, you need to draw the null lines. The external line is given by dx by dt is equal to 0. That means x minus y is equal to 0. That is x equal to y. So this is the external line. X minus y is equal to 0. Then the binary line is x plus y is equal to 0, which is this line. Right. So now we need to find out what is the vector field direction in any given part. Okay. So take this expression x minus y. So on this the external plane, this external plane. So on this x dot is 0. So if you go above this line, that means y is greater than what it normally is. So on this, at this point, let us say x and y are such that x equal to y or x minus y equal to 0. Now if you increase y further, this expression will become negative, right? So what that means is, at all the points above this null line, the x null line, x dot is negative, right? So which means, so now since the two null lines divide the whole phase plan into four parts. This is one part, this is one part, this is another part, this is another part. So basically you have two lines which divide the whole phase plan into four parts. And within each part, right, the signs of x dot and y dot won't change. Because for the sign to change, it has to go through a zero. Zero means null line, right? So therefore, if you are not crossing a null line, your sign will not change. The magnitude will change, but sign will not change. So therefore, the overall flow direction will be the same within any of these regions. Unless you cross a null line, the overall flow direction will not change. Okay, so therefore, so above this null line, x dot is negative. So both in this quadrant and in this quadrant, in this part, x dot is negative. So therefore, contrarily, below the null line, x dot should be positive. So in this part, x dot is positive. In this part, also x dot is positive. Okay, so just with one observation, we're able to say something about the sign of x dot in the entire phase plane. Okay, similarly, now let us look at y null line. Y null line is given by this line, x plus y equal to 0. So on this line, y dot is 0. Therefore, if you go above that line, right, this becomes positive. X plus y becomes positive if y is increased beyond this level. So therefore, here y dot is positive. That means in this part y dot is positive. In this part also y dot is positive. Therefore, if you go below the y null line, y dot will become negative. So in this part y dot is negative. In this part y dot is negative. So you have divided the phase plane into four parts. In each part, now we know the sign of x dot and y dot. So in this part, x dot is negative, y dot is positive. In this part, x dot is positive, y dot is negative, also positive. In this part, x dot is positive, y dot is negative. In this part, x dot is negative, y dot is negative. So you have kind of four combinations, different things happening in different parts. So now if you look at the direction, here x dot is negative, so its flow is going leftwards. Y dot is positive, so flow is kind of going upwards. So arrow will be like this everywhere. In this part, x dot is negative, y dot is also negative. So flow is going leftwards and downwards. In this part, x dot is positive, y dot is negative. So flow is going rightwards and downwards. In this part, x dot is positive, y dot is also positive. So flow is going rightwards and upwards. So if you see that, you kind of see how the flow is circulating around this point. Most probably it is there must be a kind of unstable focus. I'm guessing. I need to look at the eigenvalues in the origin. That's why you see kind of a circulating flow around it. So basically, through these kinds of very simple loose arguments, you can get an intuitive picture of the flow pattern in the entire phase plane. All right. So let us do that for a more complicated case, which is nonlinear, which is actually, it is, I think it's also shown in Strogatz. I think it's a model of glycolytic cycle. So it shows oscillations, right? So the equations are given by x dot is equal to minus x plus ay plus x square y. Y dot is equal to b minus ay minus x square y. So x and y represent concentrations of two chemicals. So therefore, both are positive. And a and b are also positive. Okay, so so now how do you proceed? How do you find out if there is a limit cycle here? We'll apply Poincare-Benedixson theorem. That means we'll construct two contours in such a way that for the outer contour flow is inwards and for the inner contour flow is outwards. How do we do that? First of all, we need to find out if there any what is the overall flow pattern using similar arguments that we have shown just now. So what we'll do first is look at the null lines. For the x null line, x dot equal to 0 means you can easily show that x dot equal to 0, x dot is this. So this I can write like this. Okay, so x dot equal to 0 means y equal to x by a plus x squared. Because this has imaginary roots, so it is no use. Because phase plan, you have to draw everything pictorially. You can't show imaginary solutions. Okay, then for y dot is equal to 0, I get this. Again, same story. So, so the root, so this equal to 0 means y equal to b by a plus x squared. Okay, so y equal to x by a plus x squared, that is the x null line, and y equal to b by a plus x squared, that is a y null line. So if you plot these two, you will get these are the null clients. So the first one is x by a plus x squared, that's x null client. That is this curve, which starts from 0 because x first as x0, this becomes 0, goes to a peak, and for x infinity again denominator dominates, so again goes to 0 at infinity. The other function is b by a plus x squared. This is a y null client. At x equal to 0, this is b by a, so this value here is b by a, and x into infinity it goes to goes to 0, so this is the y null client. And you see that there's one intersection point. That's a fixed point. So we'll see what it is later. Now we need to understand what is the flow pattern everywhere in the phase plane, only in the first quadrant, because in this case x and y are assumed to be positive, so therefore we don't have to worry about what it is like in the other quadrants. Now you see that these two null clients divide the whole phase plane, which is just the first quadrant, into 4 regions. This one, okay, this whole biggest area, which is infinite, and this one, right? And within each of these regions, the flow will have the same general direction. It doesn't change because x dot and y dot don't change sign within the region. They change sign only when you cross a null client. Okay, so it's easy to get an overall flow pattern. So now, just like before, we need to find out what are the signs of x dot and y dot within each of these regions. So let us look at that. If you take the x dot equation, right, it is like this. So y minus x by a plus x square equals 0. This is the external plane equation. So therefore, if you look at this expression, if you increase y further, right, this quantity is going to become positive because y term is positive here. Therefore, above the external plane, x dot is positive, and therefore, conversely, below the external plane, right, x dot is negative. So let us show that here. This is the external plane. Above the external plane, x dot is positive. So that means here and also here. And below the external plane, x dot is negative. So that is here and here. So similarly, now let us look at the y null plane. In y null plane, the equation is b by a plus x squared minus y is equal to 0. So if you increase y, that is go above the curve, increase y. Since y shows up as a negative term here, if you increase y, this whole thing is going to become negative. So therefore, for the y null plane, if you go above it, y dot is negative. That means here it is negative and here also it is negative. You see that. If you go below this curve, y dot is positive, and conversely, and also below this curve here, y dot is also positive. So now you got the answer. That is, in this part, x dot is positive, y dot is negative, right? So which means flow is rightwards and downwards. In this region, x dot is negative, y dot is also negative. So its flow is leftwards and downwards. In this, x dot is negative, y dot is positive. That its flow is leftwards and upwards. In this part, both x dot and y dot are positive, which means flow is rightwards and upwards. So you can see that there is a kind of a nice circulation of flow. And you can also notice that since this is a y null plane, y dot is 0 by definition, and therefore there is only x dot. So the flow on this null plane is towards the right and horizontal. Similarly, in this null plane, this is x null plane. So x dot is 0, so only y component is there, and that happens to be downwards. And similarly, on this null plane, x dot is leftwards, okay, and because x dot is negative here, and here y dot is positive. So that you can see a very clear circulating pattern. So, but that's only a starting point. You need to actually be able to construct a contour, right, in such a way that on the outer contour flow is inwards and near contour flow is outward. So it's a bit elaborate. So just bear with me a little bit. So what they have done in this worked out example in the textbook is they found a very interesting contour. You see this dashed line, which is a polygon, right? This is the contour which satisfies our requirements. So part of this contour aligns with the x and y axis. So let's look at the part which is along x axis, and we know that in this part x dot is negative, and y dot sorry, in this region y dot is positive. So which means, so this x-axis part is inside this region, right? This region. So therefore y dot is positive here, which means all arrows are pointing upwards, which is what we want. So as far as this contour, this part of the contour is concerned, arrows are pointing in from outside in, which is what we want. Similarly, if you look at the vertical part of this contour, that means the part which is a part of the y-axis. So you can see that the x dot is positive. That means within the inside this region. So therefore, all arrows will be pointing rightwards on this y-axis, which is what we want, because the rightward means will be inwards with respect to this contour. Now let us look at the horizontal contour, but let us look at only up to this point. This point b comma b by a. Why is that? Because if you look at the expression x dot minus of minus y dot, you get, so if you do all this, you get this, right? B minus x. So so I take up to this point, and so in this whole region y dot is negative. That means arrows are pointing inwards. So up to this point, so if you take this horizontal line, arrow is pointing inwards. So therefore that is satisfied. Now you take from this point onwards, so draw a line, right, of slope -1, right, and extend it until it intersects the external line. Now what we need to show is on this part of the contour, the flow is inwards. How do we show that? Now take this expression x dot minus of minus y dot. If you do this, you get b minus x. Now you see that here we have, so this is b, right? So we have taken this outside b, so that means x is greater than b. Therefore, b minus x is negative. So therefore, if x is greater than b, b minus x is that means b minus x is negative. X minus of minus y is less than 0. That means x dot minus of minus y is 0. That means x dot is less than minus y dot. Now y dot has a negative sign, minus is negative here. So what this means is, so minus of y dot means the magnitude of y dot, because y dot is negative. So what this means is my x dot is positive. Therefore, the magnitude of x dot is less than the magnitude of y dot, right? So what this is saying is, this vector has two components, x component, y component. X component is rightwards, y component is downwards. The y component is greater than the x component, right, in the length, right, in its magnitude. What does it mean? The slope itself is slope -1. Therefore, if y is more than x, it means the arrow is cutting the slope and pointing inwards. It dips more than the slope. Okay, so using a very complicated argument, they have shown that for this part of the contour, arrows are pointing inwards. Now we are left with this part. And this part, right, partly lies in this region and partly lies in this region. So if you see in both regions, the x dot is negative here and x dot is negative here, which means arrows are pointing leftwards. Here it is pointing left, and this small stretch also is pointing left. So now we have proved that everywhere along this contour, which is chosen very carefully, very judiciously, the arrows are pointing inwards. That is one thing. Now we need an inner contour where the arrows are pointing outwards, so that there is no fixed point and you don't get stuck inside fixed point. So how do we do that? There's only one fixed point in this system, which is this point. If you can show that that fixed point is unstable, okay, that means it will repel all flows away from it. And then what you do is you put a very tiny circle around that fixed point. Show that it's unstable, put a tiny circle around that fixed point. Then obviously all flow will be pointing outwards, right, or inwards into this annular region R, right, and the theorem conditions are all satisfied. Then the theorem basically says that there is a limit cycle. So how do you, now you need to show that this point is an unstable point. So how do you do that? First of all, what is that point? How do you solve for that? So to solve that, you find intersection point of the two null points that is given by this. Therefore, x equal to b, cancel the denominators. If x equal to b, then y equal to b by a plus b square. So you can solve the two equations and get this. So now at this point, you need to linearize the system and find the Jacobian that happens to be this, and plug in these values b and b by a plus b square in this expression. Calculate determinant, calculate tau, right? And it turns out that the fixed point is unstable for tau greater than 0 and stable for tau less than 0, right? And the dividing line tau equal to 0 occurs when this happens, and that curve happens to be this curve. So this is the AB space, right? So within this region, the shared region, the fixed point is unstable. Therefore, you'll have a limit cycle, and outside this, you have a stable fixed point. Therefore, you have no limit cycle. So like that, it's pretty elaborate. So you need to use, you need to use different your intuition of the vector field and construct these two contours. So using Poincare-Benedixson theorem to find out limit cycles is a bit difficult, but it's a very interesting approach. Okay, so then I'll come to the last method, finding limit cycle generation by bifurcations. So what we'll do is we'll start with basically what this says is, bifurcation means as you vary a parameter continuously, at certain critical values of the parameter, you'll see a sudden change in the dynamics, a qualitative change in the dynamics, right? That kind of a change is called a bifurcation. Okay, and the parameter values where such changes occur is called bifurcation points, right? To give an example, let us take the simple harmonic oscillator, and I've put a new parameter gamma here. Right now, I can convert this into two variables, x dot and y dot, like this. And if you solve for it, and eigenvalues will be plus or minus I omega root gamma. Right now, if gamma is negative, right, you get something like this. You'll have two real eigenvalues. One is positive, one is negative. Therefore, it's a saddle node. For gamma is positive, you get two purely imaginary eigenvalues. Therefore, it is a center or it's oscillated. So in this simple example, you can see that as you vary gamma continuously, for gamma less than 0, up to 0, there are no oscillations. Moment gamma crosses over to the positive side, you will start seeing oscillations. Okay, so that is a simple example of how by a bifurcation you can produce oscillations, but it's a linear system, it's not limit cycle. I just want to give an idea of how in a bifurcation you can see oscillations. Now, for limit cycle, let us look at one important kind of bifurcation shown in these two examples. One is called the supercritical Andronov half bifurcation, and this other one is subcritical Andronov half bifurcation. So in this case, basically the eigenvalues will move from the left half plane to the right half plane, right? And so an example set of equations which show this kind of a bifurcation is this. This is very similar to the half oscillator we have seen before. The only difference is, for the theta equation earlier, we just had omega. Theta dot is equal to omega. That was what we had before. Now there's an additional term called BR square. So that means R also determines omega. Okay, so the first equation is very similar. Here it is R into mu minus R square. Okay, so that it looks like this. So you can see that for mu less than 0, there are no roots other than there's only one real root, which is at R equal to 0. The other roots are imaginary, so you cannot show it in the graph, right? So the graph R dot versus R looks like this, right? So this point will be a stable point, and so no matter where you start from, R goes to 0. So there's no oscillation, right? So now if you change mu to positive, go from negative to positive gradually, moment mu cross out to the positive side, okay, this graph looks like this, becomes like this. So now the roots of this system is, there's a one root at the origin, R equal to 0. Then two roots plus right at plus or minus mu. So one is here and one is here. So since R is positive by definition, because it's a polar form, right, there's only one root. And it turns out that origin is unstable, this is stable. So you'll have a limit cycle of value of size mu, because R is positive. So as you increase mu, R will vary as the root of mu, right? Because this is, sorry, so this is actually root mu, so this is not mu, it's root mu, because it's mu minus r square. And you can also show that at that point your eigenvalues change from left half plane to right half plane, because as mu goes from negative to positive, you can see that the eigenvalues are this, right? And so for mu less than 0, it's a stable focus, and mu greater than 0, it's unstable focus. Origin is unstable focus. So therefore, for mu greater than 0, this becomes unstable, and this is stable. So therefore, in this case, as mu goes from negative to positive, for negative mu, there's no oscillation, r is 0. And as you increase mu, for positive mu, r increases as root mu, right? Which means at the point where you barely have produced the oscillation amplitude is 0. And as it increases further, the oscillation amplitude increases. This is a kind of a bifurcation, which is called supercritical and half bifurcation. So when the oscillation begins, right, as you vary a parameter, for up to one value parameter of the parameter, there is no oscillation. When the parameter crosses a certain critical value, here it is 0. In general, it can be some non-zero value, right? Then after that point, the oscillation starts with a very small amplitude and gradually increases. Okay, so then there's another kind of bifurcation called subcritical and half bifurcation. So this is shown by this example system, where R dot is not just a cubic nonlinearity, but a fifth order nonlinearity, right? Mu r plus r cube minus r power 5. The theta dot equation is the same. So in this case, what happens is your R dot versus R plot looks like this, because it's a fifth order system. So in this case, for mu less than 0, so the mu is here. If you make it negative, right, the system will look like this. And you can see that in this part, so it has 3 roots. R equal to 0 is one root, R equal to A, and R equal to B. So for in this part, if your R is here, the R dot is negative, so it will reduce. It will go back to 0. In this part, right, if R is between A and B, R dot is positive, so it will increase. It will go to B. So basically, no matter where you start from in the state space, R, if it is less than A, it will go to 0. If it is greater than A, it will go to B. It will never stay at A. Right? Therefore, R equal to A, which is radius A cycle, is an unstable limit cycle. R equal to B, which is radius B cycle, is a stable limit cycle. And R equal to 0 is not a limit cycle, it's a fixed point. It's a stable fixed point. So basically, you'll have a system which looks like this. There is a stable limit cycle B, unstable limit cycle at A, and there's a stable fixed point. So what happens when you change mu from negative to positive is, this unstable limit cycle becomes smaller and smaller and merges, right, with this fixed point, leaving there's only one limit cycle is left at that time, where R dot is unstable, so it cannot stay here. It gets repelled away from the origin, and R equal to B is stable limit cycle, which is like this. Okay, so that gives a very nice example of a limit cycle which is born out of a bifurcation. Here again, there are 2 varieties, subcritical and supercritical, right? And so one thing is interesting about this subcritical is, as you increase mu and take it from negative to positive, unlike the previous case, it won't start from an infinitesimally sized limit cycle. It starts from a finite size. So if you see that kind of behavior in a real oscillation, it means you are looking at an Andronov supercritical bifurcation. So let us stop the discussion of limit cycles there. In the next class, we'll go back to neurons, right? We'll study a certain neuron model called Hodgson-Huxley neuron, which is a very important neuron model, one of the most important neuron models. And Hodgson-Huxley were awarded Nobel Prize for that work. So let us formulate that model and simulate that model and try to understand how it works.